Okay, well, let's go ahead and get started. I'd like to welcome Tom McCord, who's giving our applicant seminar today. Tom is one of the pioneers of our profession and has been on everything, doing everything. And he recently in geological standards, set up the Bearfight Institute up in the Methow Valley in Washington, where he's currently living. And it's a real pleasure to have him here talking to us today. So Tom, I'll turn it over to you.
Okay, thank you, Mark. Yeah, I'm Tom McCord, and it is a pleasure for me here this morning to be able to talk to you about my favorite object in the solar system these days, which is Ceres. Now, how do I make this thing go forward? Advance. Why doesn't it advance? There it goes. It's just slow.
There we go.
Yeah, we just completed a detailed study of Ceres using the Dawn spacecraft and have vastly increased our knowledge of the object, this warm, wet object. What I say here today is strongly dependent on the contributions of the Dawn science and engineering teams. So in a way, I'm standing on the shoulders of many giants. The Dawn spacecraft itself was unusual. It used ion propulsion. Xenon ions accelerated an electric field created by solar power. There were 4 spacecraft investigations. One was a framing camera, which imaged surface features and focused on geology. There was the visible and infrared spectrometer, which measured the spectrum from 0.3 to about 5 microns and determined mineralogy and the molecules composing the surface. There was the gamma ray and neutron spectrometer called GRAND, which was sensitive to elemental composition, particularly hydrogen. And I'll get into that in a minute. And finally, the gravity field measurement using the radio science for studying the interior. Now, we knew something about Ceres before the Dawn mission using ground-based telescopes and modeling. And these early findings motivated and justified the Dawn mission. A few statistics. Ceres is about 1,000 kilometers in diameter. It's the largest object between Mars and Jupiter in the asteroid belt, and has a density of about 2.1, which I'll come back to in a minute. The early spectral observations that were made of Ceres gave us some understanding of what its composition is, and that implied something about its evolution. The early work showed that the surface is composed of altered minerals, clay-like minerals, and that it seems similar to primitive carbonaceous chondrite meteorites, but not exactly the same. There were also H2O features and OH features observed in the 3 micron spectral region, which again suggested altered minerals and maybe even the presence of hydrated minerals. There were studies continued after those early observations and developed more and more specific determination of the minerals, some of which were incompatible chemically. That is, you couldn't have them all in the same chemical environment. But nevertheless, they basically just reinforced the earlier measurements and the early interpretation of a hydroxylated, hydrated surface like clays and some spectral neutral agent like carbon, and similar to, but not exactly the same as carbonaceous, primitive carbonaceous chondrite meteorites. This also motivated this study of the evolution through using thermodynamic modeling. And of particular motivating factor was Ceres' density of 2.1 or 2100, depending on which units you're using, which put it between water ice and a basaltic composition like Vesta, in between it in density. So what you assume to be the density of the non-ice fraction, there had to be about 17 to about 27% by weight water composing Ceres. This made it, of course, a very interesting object. So the thermodynamic modeling was based on the assumption that these two components accreted cold and contained CAIs, the calcium aluminum inclusions, which had the energy, the radioactive nuclides, to cause a thermal evolution of the object. So Ceres warms up, the ice melts, and water circulates through the silicates. Low temperature alteration quickly follows, and you end up with a hydroxylated altered material and water, if there's some water left over. And if you use serpentine-like reactions, you have a lot of water left over. So there is some differentiation that was predicted, and that the water, leftover water, would rise and the silicates would sink, and you would have both chemical and some gravity differentiation. Of course, there's infall material contaminating, if you will, the surface, and the surface itself remains solid because of the cold space, but would be gravitationally unstable and would, at the slightest chance, such as through impact, founder and would mix. So the surface would be mixed many times, probably. This led to a prediction of models for the interior following the evolution. The two extreme models, one would be a undifferentiated object, this an altered object, unmixed. The other extreme would be the hot object, which would, or the hot evolution, which would be an object with a metal core and purely differentiated with the wetter materials near the surface. In between that is a more moderate possibility, which would be an interior of altered silicates and a wetter, salty, perhaps liquid deposits above it in two different forms. And this is in fact what we found. So a summary of the knowledge before dawn was a composition of aqueously altered silicates, similar to primitive carbonaceous chondrite meteorites, and an interior with a water content in some form of 17 to 26% or so by weight water, differentiated to some extent, and may still have liquid water. So as I said, this is the basis for justifying selling, if you will, and then planning and implementing the Dawn mission. So we seem to have here a textbook example of a geochemistry-driven evolution. A small object, but with sorry, this thing keeps jumping around. A small object with major planetary processes controlled by the presence of water. The water controls the temperature and the chemistry, as evidenced in the minerals formed, and the geochemistry then controls the geophysics and geology. So Dawn's findings. Dawn had several different missions. There was the primary mission, where it orbited Ceres at several different altitudes and produced near global coverage at several resolutions. There were then two extended missions. One was basically to pick up the observations that weren't possible under the primary mission, in some cases due to the advancement of seasonal lighting on Ceres. And the second extended mission, XM2, was particularly exciting because we made the orbit much more eccentric, and the pericenter there was very low, about 35 kilometers altitude, and migrated. Here's a plot that shows the pericenter position, starting on the upper right, just north of the crater Okatar, which was one of the prime targets, and passing over Okatar, down to the South Pole, and then back up north to mid-latitudes, where the mission ended because the spacecraft ran out of hydrazine and could not orient itself anymore. The reds and orange colors here around the black dots are in the region where the gravity measurements were most precise, and detailed study of the crust and mantle were then possible. And I'll discuss that shortly. So let's look at what Dawn found. And the mineralogy is the first important part of it. And again, hydroxylated silicates are dominant, but in the Dawn case, we have a much more detailed understanding. Dominant altered silicates are ammoniated clays and magnesium phyllosilicates, carbonates, and a dark component. Surprising, the ammoniated silicates were most surprising, although there was a ground-based study that did propose that. Trudy King and Roger Clark was part of that in 1980s, I think. Also salts, magnesium and sodium carbonates, and actually NaCl. These are all evidence of global advanced aqueous alteration. Let's look at two of these mineral types, the magnesium phyllosilicates and the ammoniated phyllosilicates. 2.7 micron band and 3.1 micron band are the evidence of those two. Let's just for a minute advance ahead and look at that. Here's an average spectrum for Ceres in the 2 to 4 micron region. And here's the 2.7 band and the 3.1 band phyllosilicates and magnesium silicates. Now, again, a bit of a digression. If we look at the very early telescopic spectra of Ceres in the visible to about 4 micron region, I've plotted them here. Actually, Jean-Philippe Combe prepared these slides. And the spectra are offset to better see the features in each one of the spectra. And they're kind of a mess. And this illustrates the primitiveness of the technology and the tools in those days. Nevertheless, you can see some features like the 3 micron region feature here that appear over and over again. It's a little difficult to identify very specific minerals here, but there's little doubt that there are altered minerals on the surface with the presence here. And in the visible, you see very little structure, which is in fact what Dawn found too. Coming back to the 2.7 and the 3.1 band, that is the distribution of magnesium and ammoniated altered minerals. Here's a plot of the, well, first of all, the band positions do not change all over the planet, which means the composition of the minerals is pretty much constant everywhere. Secondly, the amount of material in each of these, identified by each of these two bands, varies some, but in coordination. So there's more or less of these materials, more or less correlated, but no change in the mineralogy. So the aqueous alteration process was global, was endogenous, and not due to some local strange environment. Here's a correlation plot, again, prepared by Jean-Philippe, and it's a map of both the two bands, and this is the correlation plot. So you see that they do vary in a correlated way, somewhat fuzzy, but they do. In addition to the ice, we find water ice, actually water ice exposed on the surface in a number of places. This is very important because water ice, the lifetime exposed on the surface is relatively short. It obviously depends on how much is there and how much illumination it gets, but on the order of 100 or 1,000 years, way short for geologic timescale phenomenon. And most of, or all of them, are at higher latitudes and in regions of near permanent shadow. So it looks as though there are these lenses or deposits of water ice mixed up in the crust. The grand investigation, as I mentioned earlier, was particularly sensitive to hydrogen and to the upper meter or so of the surface. Here's a plot, a map of hydrogen in the upper meter of Ceres, and there's more hydrogen at the poles and less at mid-latitudes, which suggests more water ice near the surface at the poles and less at the lower latitudes, which is what you intuitively would expect. Further, the Grand was able to detect and map some mineralogy or some elemental composition, and find that compared to primitive chondritic composition, it suggests that the surface is a little different than the interior, which again suggests differentiation of a chemical nature. So now the crater statistics. Mike Bland in 2013 published an article predicting that the crater statistics versus size would be a measure of the flexibility, the viscosity of the surface. And he was right on. Here is a plot of the crater, cumulative number of craters versus diameter as found by Dawn. And you can see the saturation line, the solid black line, where the surface is saturated at that crater diameter. And as you go up in crater size or go right on the plot, you can see around 80 or 90 kilometer diameter crater that you start to have a less than saturated number of craters. And so this suggests, and in fact, if you use like Vesta as a model, there should be 6 to 12, 10 like large craters larger than 40 kilometers. And in fact, there are none on Ceres. Maybe 1 or 2 remnants that you could argue was once a large crater, but basically none. So this suggests that the large craters have been absorbed by the surface. The surface is plastic enough to absorb them. And this again suggests a wet or a none, that's not right, a not so strong surface, particularly deeper. Surface features. There are quite a number of really exciting surface features. I have to start with Okatar crater and the bright high albedo spots in it. We saw these almost from the first global image that Dawn was able to get. And my first reaction was salts. There's the salt deposits from the aqueous alteration. And in fact, that's what they are. In Okatar, we see in the central pit of the crater a dome, which is in fact salt minerals. And very exciting, if you look up close in the XM2 mission, near features that look like vents, there are hydrated NaCl, according to the Veer measurements. That hydrated NaCl is not stable for very long on the surface, again, in the thermodynamic conditions there. And so you can argue that this is a very recent deposit, that Ceres is still active, and that the brines are being ejected from the vents and deposited nearby, and then slowly disappear. And then here's another view. You can also see in this view the mass wasting and the flow-like features in the surface. So the surface material is rather fluid. Flow features. There are quite a number of obvious flow features in the surface. Here I show one, Julian crater, and in fact, up in the north is up in the lower plot. There is a water ice deposit up there in more or less in near permanent shadowed areas. There are many more of these. Here's an example of 3 different ones. There's a publication about 2017, of a study of these different flow types. Basically, they differ by what the viscosity, how rapidly they flowed, and what the water content was of them. Hunmans. Another startling feature, it's a protrusion, again, of aqueously altered products above the surface, quite young. There's very few craters on it. It's very difficult to date using crater statistics. It just jammed up through the surface. From all of these different features, and particularly from the gravity studies, a model of the interior has been developed, and that consists of a crust of something like 40 kilometers thick, higher strength, lower density with on this lower density as you go deeper, but less strength. And below that, a mantle which goes down at least to 100 kilometers. There could be a core, but the observations just aren't detailed enough to support that, so it cannot be confirmed. So based on the gravity topography, the crust with depths increases with density, as I said, decreases in porosity, or increases with more rock and salt. And near the surface, there's a greater compensation for any density differences. Models of the Okatar crater have been interpreted to suggest that the salt deposits in the crater are the result of accessing brine reservoirs deep in the crust, and that there may have been some fractures or disruptions in the crust earlier that allowed this access to brine deposits at the base of the crust. And further on this, there are, again, at XM2, detailed studies of the gravity and density structure. It's found that it is somewhat mixed up. That is, there are anomalies which could be explained by a series of percolations of brine and altered material intrusions into the crust. So this is pretty much what I was saying, and the Anami Planum is the region that Okatar is in. This seems a case study for what probably happened in other places on Ceres. So again, we confirm, and with much more detail, see that this is a geochemistry-driven evolution controlled by water, where the presence of water controls the temperature and the chemistry and the geology and geophysics that involve. Now, I've given a summary of where we stand with Ceres. There are some recent publications that anyone who wishes to further read or study this topic can go. There is an end of mission study published in the journal Geochemistry, or about to be published. A number of us put this together. It's, as I say, in the journal Geochemistry. It's in press. Is to be published, I'm told, any month now. I have an in-press copy that I can provide for anyone who is particularly interested in this. Before this, there were two Icarus and one MAPS issue, an entire issue on, number one, the surface composition of Ceres, on the geology of Ceres. Dave Williams led that one, and on the interior Ceres that Hap McSween led, that Julie and I have an article, the lead article in that. So there's a lot of more resources than what I've just summarized, and let me know. I can get you a copy of the geochemistry article that's not yet published but will be any month, and the others are available in the literature. So stay tuned. There's still much more analysis to be done, but that's sort of where we stand at the moment. Thank you. Anybody left out there?
Unmute here. Thank you very much, Tom. It's just, that's such a great mission. And there's still so much more to be drawn out of it. Anybody have any questions for Tom? Go ahead and unmute and ask.
Hi, Tom. This is Roger. Can you hear me?
Yes, I can.
Great talk.
Thank you.
Couple of notes. Yeah, could you send me your in-press paper on that Icarus paper? I haven't been up on Ceres composition. Just a side note, the King et al. Ammonia detection, I did the fitting of the absorption bands, and it was one of the best fits I'd ever done by that time. And so I was always very confident that it was correct, more correct than many other of the interpretations I've done over my career. So I'm glad it finally got accepted, because we got a lot of flack for that when it first came out.
Yeah, probably by me too. but you were always so confident about everything, Roger. It's hard to, you were right about this. There's no question. And you always were adamant about it. So I'll hand it to you there.
Well, and another side note, the scapolite on Mars controversy, that was a great fit too, but and I reported this in some presentation somewhere, I forget where, but the scapolite reference spectrum that we had, the sample was contaminated with prehnite. And so then we went to the prehnite type location, which is Patterson, New Jersey, got samples there, and those samples of prehnite were contaminated with scapolite. But so the scapolite feature was always prehnite. So it was an XRD failure.
Yep.
Hey, Tom, it's Tom. Nice talk. Just curious. You mentioned.
Thank you for your help. You're partly responsible.
Okay, I accept that responsibility. Let's see. So you mentioned the detection of hydrohalite in Cerealia facula.
Yes.
I'm just wondering, as a spectroscopist, you've looked at their paper and how they came to the conclusion that there would be hydrohalite there. How robust do you think that detection is?
That's a can of worms. That's a really deep and difficult question. And I'd like to maintain colleagueship with everybody. With a number of these spectral interpretations, I think there's room for, how do they say it, further study. I'm not saying they're wrong. I'm just saying it's difficult with these very complex absorptions to be absolutely sure. So I would not call any of them wrong. I would just say there's certainly room for more study.
Well, NaCl doesn't have any absorptions in the
No, it's
visible near infrared, so it'd just be
right.
water bands.
That's exactly right. Roger's right.
So
I'm sure
isn't the
he's always right,
interpretation,
but
because there are no other absorption bands, it has to be some a molecule like an NaCl, so you're only seeing water bands.
yeah, the salt that you're dealing with does to some extent affect the water absorption bands, but you are seeing the water absorption bands, not the sodium and calcium or whatever salt. And that's part of this uncertainty. You know, it's really difficult to be absolutely certain with these altered minerals because you're seeing secondary effects. But
and these things change with temperature. Do you have good temperature measurements on Ceres to know what temperature your lab spectra should be done at?
Yes, to the extent that matters. For some, it's temperature dependent, the absorptions are. For other salts, not. And the uncertainty in the temperature on Ceres for the temperature dependence that I'm familiar with isn't enough to make a difference.
What kind of temperatures are we talking about?
160, 180.
Okay, thanks.
Any more questions for Tom? Tom, thank you very much. It's a real pleasure. And, we'll be in touch.
Great. Yeah. Thank you. It's great fun to talk about this stuff.
Yeah. Wonderful to hear about it.